Hey folks, so this is that kind of optional video showing where these equations for Unit 1 in our AP Physics 1 course come from. And I already kind of hinted in class that these actually come from calculus. So this is really just a calculus derivation going through and explaining where the heck these equations actually come from. How did we get them? Did they just pop up out of thin air? No, they're from kind of some high-powered math, but it's actually pretty quick, pretty straightforward. So I've gone through and I've kind of used my rainbow pen here to kind of number them. We have equation number 1, 2, and 3. And we're maybe getting a little familiar with them, or we've at least kind of seen how they work a little bit. And we kind of have to go back to our basics. We know that x really here is our displacement. I think on your equation sheet it says position. Velocity is this rate of change of displacement per time. But in a calculus sense, if you wanted to get the instant velocity, it would just be like an infinitesimal little tiny dx and a little tiny dt is the whole idea behind that, okay? So we're not going to use this as kind of the slightly yet less advanced version. So really velocity is dx dt, and acceleration similarly is not delta v over delta t, it's dv dt. And so really I'm going to go through and explain how to get our first equation here, this equation number 1. So it's all going to start really with a is dv dt. And all I'm going to do is multiply my dt over to the left side. So now I have a dt is equal to dv. The neat thing is I'm going to integrate now both sides. So I'm going to go over here and I'm going to integrate the left side. Ooh, that was a bit of a kind of a gnarly integral sign. It's been a while. Maybe we get a couple practice runs on here. And we're going to go from some time naught to some final time. And now we have a dt. And then on the right side, we just have, well, we're integrating the velocity from some initial velocity v naught to some final velocity v. And we just have our dv. And then really this just becomes, in kind of a simple way, we just get a t kind of evaluated at this lower and upper limit for time. And then we just have v, which is also evaluated at some lower and then upper value. And so really as I go through with this, we can kind of scroll down now a little bit here and hopefully kind of fit everything all at once. Well, we just have a t minus t naught is equal to v minus v naught. Now, if the initial time is 0, well, obviously this thing goes away. So we just have a t is equal to v minus v naught. Well, I'm just going to rearrange a little bit here, and I'll just add my v naught over to the left side. So now I have v naught plus at is equal to v. And if we can kind of check it out now, really, we've kind of cleaned it up some. This actually is our equation 1. We have, oh, where did my mouse go? There we are. Vx is equal to Vx naught plus Axt. So I just did not use little x subscripts on it. And we can, I guess, if we really want to kind of do a little rearrange here, call this all in the x direction. And then we just rearrange, just flip the sides. Vx is equal to Vx naught plus Axt. There we go. First equation we've derived just from the fact that acceleration is just dv dt. Now our second equation, let's use blue for this one. We're going to use actually the fact that velocity is dx dt is the whole idea. So maybe I can fit this one a little smaller. If v is just dx dt, I'm going to do the same trick. So now I'm going to multiply the dt over to the left side here, and we'll have that v dt is equal to dx. Well, let's integrate both sides. So now we're going to integrate v dt from some time naught to some later time, kind of as our upper limit. And we'll do we'll integrate dx. Whoa, that was a little weird. Wonky, sorry about that. Oh, it's that shape kind of forming part. And then we have our x naught and our x, kind of our initial and final displacement, really. So now looking at this, we're going to just end up having, of course, well, we'll get our VT. But I want to do something weird here, actually, and I'm going to kind of switch colors. We're going to plug in from equation 1. So what I'm really going to do is I'm going to take what we got for V, and we might as well be calling this, I guess, Vx, really. So I'm going to take this whole thing here, and I'm going to plug it in up there. So I'm actually going to have this integral from t naught to t, and now my Vx actually is really this Vx naught plus ax t, where again, velocity or speed, acceleration, and time, and then dt. And we're still integrating this right-hand side in regards to x, just like that, which is kind of neat, right? So now what we can do is we can kind of integrate this term separately from this term, and we'll end up getting some kind of neat stuff now. We're going to actually get our equation 2. So if I integrate this right side, well, I'm going to have Vx naught t here, Vx naught t plus, and now I'm going to have 1/2 ax t squared, because the integral of this ax t is going to be 1/2 a t squared, really. And this is again going to be from our t naught to t. And then the right side, well, if we just integrate this, I'm going to skip the step. We're just going to have x, right? And we're going to have the integral of x, and we're going to evaluate it from x to x naught. So I'm really just going to have x minus x naught. And so now what I want to do is, let's say, for sake of the fact that we can kind of choose when our time starts, even if I'm really looking at like, oh, I'm going from 2 seconds to 100 seconds. Well, that's the same thing as saying 0 to 98 as far as how much time has passed. So let's just call this t naught 0. All right, and it'll make life a lot easier. Okay, now we're not going to have to do all this subtraction stuff. We're just going to have literally Vx naught t plus 1/2 ax, a in the x direction, t squared, equals x minus x naught, which is kind of neat. So again, we're pretty close, actually, if you're paying attention. We're trying to get this thing. So now I'm just going to massage it into shape. I'm going to start and get my x alone, and then I'll kind of go in with increasing values of t, is the whole idea. So all I'm going to do is I'll have my x over on this side. Actually, let's kind of start from right to left. So I'm going to just rewrite it and kind of manage the form a little bit here. I have 1/2 a in the x direction t squared plus Vx naught t, and then if I add this x naught over to this side, plus x naught equals x. And now, of course, my sides are flipped compared to our AP equation, but we still see that the final x value is equal to the initial plus Vx naught t plus 1/2 at squared. This is the same thing. If you wanted to go nuts, you could subtract this over to the left side, and you could subtract all these to the right side, and you could cancel all the negatives, and you end up getting x is x naught plus Vx naught t plus 1/2 a in the x direction times t squared. And that is, in fact, our equation 2, which is kind of neat. So that's where that one came from. We actually just integrated this second kind of fundamental equation for it there. And this was really what we used for our first equation. So now let's use a different color again. And the thing I want to pause and mention here is average velocity. This is actually what we've been doing for most of the time in our class, and I'm just not calling it such. But this really is finding the average. If you know what the final value is, and you know the initial value is, and you kind of divide it, this is really finding the average velocity. Taking this derivative is really going to be what finds that instantaneous velocity to later time. But as we get these x and x naught values closer together, and these t and t naught values closer together, it eventually kind of does become, right, from your calculus class, our instantaneous value. But I want to use this average velocity thing now, and this is what we're going to kind of play around with, okay? And so what we're going to do, we'll start with this. We'll have our average velocity, that's what this little bar on top means, is our our final displacement minus our initial divided by our final time minus our initial time. And let's again assume that we're just going to call the initial time 0. So this kind of cleans things up a little bit for us. And again, that little shape forming thing there, let's turn that off again. And we have just this difference between our final and initial displacement and our time. Okay, now I'm going to take this and I'm going to multiply t over to the left-hand side, okay? So now we have our average velocity times time is equal to the final minus the initial displacement, okay? Now, we're going to have to do something a little weird here. We're going to make an assumption, okay? So the assumption is that the acceleration is constant. So my average velocity, this is saying that like this thing is speeding up over time. If it starts at 0 and then it ends at 50 miles per hour, let's say, because that's a unit we're familiar with, maybe the average speed then, if you kind of looked at it all, would be 25 miles an hour, right? Or something in between 0 and 50, right? So what we're going to do, we're going to make an assumption, all right? And I'll tell you that it works most of the time in pretty much all scenarios in our class. I actually can't think of a scenario where it doesn't work. And it's true if we have constant acceleration, which we'll always have. You'll never have a changing acceleration, really. So we're going to assume that the average velocity is 1/2 of our final velocity minus, plus our initial velocity. So if I ended at 50 miles per hour and I started at 0, well, 1/2 of that would be 25. We're going to make this assumption, and this works. This works if A is some constant. So gravitational acceleration is constant on Earth. Things constantly speed up, really, right? So now we're going to plug this in. So plug this in. Plug this in for the average. So really what I'm saying here is that we're going to take this thing and we're going to plug it in right there. That's what we're going to do, and that's what we're going to write on the next step. So now we have 1/2 of v, our final velocity, plus our initial velocity, okay, times t is equal to our final displacement minus our initial displacement, okay? So I'm going to clean this up and write it one more time. I'm going to take this initial displacement, and add it to this side. So now I'll have 1/2 our final velocity plus our initial velocity times t plus our initial displacement is equal to our final displacement. Now, I'm going to make a note here. This is not on the AP equation sheet, not on the AP sheet. Some of my classes in Cal Poly use this, and we were actually given 4 equations for this unit, really kind of this topic that we're handling right now. This one is not given on the equation sheet. I will not use this because I'm not expecting you to memorize it. But we need this actually to get our third equation. That's really what we're driving towards, okay? So here's what we're going to do. We want to get this guy now, all right? We want this, and we're close. We're really, really close. All we have to do is we're going to solve, okay? So we're going to solve for t, for time, in equation 1, all right? And we're going to plug that in. Oops, that shape thing again. And we're going to plug this into equation 2.5 and plug into equation 2.5. Okay, then this will be the last step. Then solve for Vx squared, because that's the format it's in here. So this is the steps. We're going to take equation 1. We're going to solve this thing for time. Once we get time alone, we're going to take it and we're going to plug it in to this equation down here. And then once we're going to have that in, we're just going to massage it. We're just going to have to do algebra, essentially. That's really all it is at this point. So I'm going to slide a little bit this way. So we're going to take equation 1. So here is my equation 1. We have Vx equals our final velocity equals our initial velocity plus the acceleration times time. Solving this for t, so I would subtract this vx over, and then I would divide by a. So I'm going to do that all in one fell swoop, okay? And I have then that t, and maybe I'll do it in two steps, I guess. I have our final velocity minus our initial velocity divided by the acceleration equals time. Okay, that's what we're going to do. And now I'm going to take this and I'm going to plug it into my equation 2.5. So I'm going to rewrite our equation 2.5, 1/2 final velocity, oops, forgot my parentheses, final velocity minus the initial velocity times time plus the initial displacement is the final displacement. And I'm going to take that value and I'm going to take this whole thing here, all right? I'm going to plug it in right there. That's the goal, okay? That's what we're really doing. And once we've done that, we're just going to solve for Vx squared to get it alone. That's it. And that's how we actually get this final thing. This last one isn't calculus. We've really already kind of done all the calculus and the hard stuff already, unless you just call this algebra kind of grindiness hard, okay? So rewriting it then, I now have 1/2 my final velocity, and this should be a plus, oops, my bad on that, plus, okay, and it's plus our initial velocity times now, and here's where it's kind of gets a little sloppy, messy looking. Now we have our final velocity minus our initial velocity over a, all right, plus our initial displacement equals our final, and yikes, what a mess, am I right? This is kind of nasty looking, I know. So I'm going to take the 2 that's in my denominator, and I'm going to bring it in here with my a, all right? And it's going to kind of help us out a little bit. We'll kind of clean things up, okay? So I'll do this kind of 2 steps at a time. I'm going to subtract this over to this side. That'll be the first thing I do, and I'll combine the 2 to being under here with the a, and I'm just going to rewrite it then. So we have our final velocity plus our initial velocity times our final minus our initial divided by 2 times the acceleration, because again, we took the 2, we brought it down there, equals our final displacement minus our initial, because I took this and I brought it over to that side, and to do that I have to kind of subtract. Okay, so that's the idea for this. Cool, let's keep going. We're almost done. I'm going to take my 2a and I'm going to multiply it over to this side. So it's going to multiply to both of these is the idea. So now I have v final, my final velocity plus my initial times my final minus my initial equals 2 times the acceleration times my final displacement minus my initial displacement. So now you're seeing we kind of have this thing at least now, okay, which is kind of cool. Now, I'm going to skip all the steps of kind of foiling first, outside, inside, last, right, all of that. So Vx times Vx, well, actually we can just write it, V final squared, all right, plus, or I guess this one would be minus, and then V final times V initial, V final times V initial, and then we have plus V final times V initial, these two right here, right? V final times V initial, and then minus, we have V initial getting squared here, V initial squared. So we can see pretty easily these two cancel out, they kind of kill each other off, and then we end up having 2 times the acceleration times our change in displacement. And so you can really see now our last step to get this is really just to bring this guy over. So that's it. We're right here. We are essentially done. I'll write it our last time because I'm just adding this guy right here over to this side. That's really all that's happening. And I have my final velocity equals my initial velocity squared plus twice the acceleration times my final displacement minus my initial displacement. And that is it. That is where our 4 equations actually come from. Hooray!